Hi students, for the coming IPE exams and board exams, let us see some important questions from States of Matter chapter. States of Matter, very short answer type of questions, let us discuss. So here gas laws are very important. They may ask vsaqs from this chapter. Boyles Law will discuss. State Boyles Law, give its mathematical expression. At constant temperature, volume of given mass of a gas is inversely proportional to its pressure. So this statement we can write in a mathematical form as V is inversely proportional to pressure at constant temperature and a number of moles. From this, V is equals to K by P, PV is equals to K, where K is nothing but proportionality constant. So this is Boyle's law. Next, Charles law. At constant pressure, volume of a given mass of a gas is directly proportional to absolute temperature. V is directly proportional to T. Here, pressure and a number of moles are constant. So here, if we remove the proportionality, then one constant we have to write. V is equals to KT. This we can write it as V by T is equals to K, where K is a constant. Next, what are isocodes? Let us see what are isocodes. Isocodes are nothing but the graph which is drawn between pressure and volume at constant temperature are called as isotherms. Simply, the graph which is obtained at constant temperature are called as isotherms. So here the graph is between pressure and volume. If you plot a graph between pressure and volume, you will get lines like this, so at different temperatures. So this is obtained at a constant temperature. Next, what is absolute temperature? The temperature expressed in Kelvin scale is called as absolute temperature. So this is represented by capital T. Capital T is equals to 273.15 plus T degrees centigrade. And T naught is equals to 273.15 Kelvin. This is at 0 degrees centigrade. Next, isobars. The graph drawn between volume and absolute temperature at constant pressure. So in this, pressure kept constant. Simply the graph which is obtained at constant pressure is called as isobars. Here the graph is between V and T, pressure kept constant. Next, let us see Avogadro's law. What is or state Avogadro's law? See, under same conditions of temperature and pressure, equal volumes of all gases contains equal number of molecules or moles is called as Avogadro's law. So which is mathematically expressed as V is directly proportional to N. So in this, temperature and pressure both kept constant. So V is equals to Kn, V by N is equals to K. Even two gases if we consider, V1 by N1 is equals to V2 by N2 also we can write. So this is the definition for Avogadro's law. Next, coming to the 9th question, that is isocodes. So the graph drawn between pressure and temperature at constant volume kept constant in this. So the graphs which are obtained at constant volume are simply called as isocodes. So your pressure versus temperature, we got a graph. This is called as isocodes. So in this, V1 is less than V2, which is less than V3. Next, 11th one, which is very important, that is what is gram molar volume? The volume occupied by 1 mole of gas at STP conditions is called as gram molar volume. STP conditions. STP is nothing but standard temperature and pressure. Standard temperature and pressure conditions are called as STP conditions. So here what are the standard conditions? 273.15 Kelvin and 1 atmosphere pressure, 1 mole of ideal gas occupies 22.4 liters of volume. Or at 273.15 Kelvin and 1 bar pressure, then 1 mole of gas occupies 22.7. Here the difference you have to observe, that is when ATM is considered 22.4 liters, we have to take 1 bar. If you consider 22.7 liters, we have to consider. So this is gram molar volume. Next, one more important question is, what is an ideal gas? Any gas that obeys Boyles Law, Charles Law, Avogadro's Law at all conditions of temperature and pressure is called as ideal gas. Or simply you can say the gas that obeys all the gas laws at all conditions of temperature and pressure is also called as ideal gas. So we know ideal gas equation also. PV is equals to nRT is the ideal gas equation, where P is nothing but pressure, V is volume, N is number of moles, and R is universal gas constant, T is temperature. So here from this we can write different terms also. That in 13th question, if you see, why the gas constant R is called as universal gas constant. Why? Because the gas constant R is same for all the gases. Hence it is called as universal gas constant. So from ideal gas equation, we can get the relation between R and different types of the pressure, volume, number of moles, and temperature. Just now we discussed PV is equals to nRT, which is called as ideal gas equation. From this we can write R. So R is equals to PV by NT. So it has values, that is 8.314 joule per Kelvin per mole is the value of R in joules. Even we can also write the values in in liter atmospheres and even in kelvins. The next it is there we'll discuss. Now let us see 15th question, that one only. Give the values of gas constant in different units. So R is equals to PV by NT. This we got from where? Ideal gas equation. PV is equals to nRT only, right? So here R has different types of values. So here it is in 8.314, that is Pascal per meter cube, Kelvin, that is per mole, 8.314 joule per mole, 8.314 into 10 to the power 7 ergs per mole per Kelvin, and R value even you can also write in calories, that is 1.987. Even you can also write it as 2 calories. Or you can also write R value as 0.0821 liter atmosphere per mole per Kelvin. So this is called as what are the values of universal gas constant, that is R. Next, let us see one more question, that is Graham's law of diffusion, which is very important question. Even it is there in the SAQ also. There also we'll discuss. State Graham's law of diffusion. So here the term diffusion is very important for the study of gases. Why? Because gases will diffuse. So at constant temperature, the rate of diffusion of a given mass of a gas is, that is the rate of diffusion of given mass of a gas is inversely proportional to the square root of its density. So this is called as Graham's law of diffusion, which is mathematically expressed as R is inversely proportional to square root of density. Next, 18th question. So this is also frequently they are asking, which of the gases diffuses faster among nitrogen, oxygen, methane, and why? So here just now we discussed the relation between rate of diffusion and density. So both are inversely proportional. The gas whose density is more, its rate of diffusion is less. So here if you see the molecular masses of these gases, nitrogen, if you consider, its molecular mass is 28, oxygen molecular mass is 32, whereas methane, that is CH4, is 16 grams. 16 grams, 28 grams, 32 grams. So among all the gases, methane molecular mass is less, so rate of diffusion is more. CH4, that is methane, diffuses faster among nitrogen, oxygen, and methane, right? This is due to lower molecular mass. So according to this Graham's law, this is about Graham's law of diffusion. Next, let us see one more question from this chapter, that is 19th one. How many times methane diffuses faster than sulfur dioxide? Sulfur dioxide molecular formula is SO2 and its molecular mass is equals to 64. And methane, its molecular formula is CH4 and its molecular mass is 16 grams. So when two gases, if they ask how to get relation between the rate of diffusion of these gases, simple, R1 by R2 is equals to under root of M2 by M1 is the formula. So here R1 is nothing but rate of diffusion of methane and R2 is the rate of diffusion of sulfur dioxide, is equals to square root of molar mass of sulfur dioxide by methane. So molecular mass of sulfur dioxide is 64 and methane is 16. So I'll simplify this. 64 by 16, that is nothing but root over 4 by 1. Root 4 is nothing but 2 by 1. That means methane, that is rate of diffusion of CH4, is equals to 2 into rate of diffusion of sulfur dioxide. Means methane diffuses 2 times faster than sulfur dioxide. So this is about Graham's law. Next, state Dalton's law of partial pressures. At constant temperature and volume, the total pressure exerted by mixture of non-reacting gases, this is very important point, that is non-reacting gases, which is equals to sum of the partial pressures of all the individual gases. So this is called as Dalton's law of partial pressure. So which is represented mathematically as P total, that is nothing but total pressure, is equals to P1 plus P2 plus P3, so on. Here P1, P2, P3 are the partial pressures of the gases 1, 2 and 3. Next, aqueous tension. The pressure exerted by saturated water vapor is simply called as aqueous tension. So this we can write it as pressure of dry gas is equals to pressure of moist gas minus aqueous tension. This is the formula for the pressure of the dry gas. Next, let us see one more important question, that is 26th one. What is Bojamin constant? So the gas constant per molecule of a gas is simply called as Bojamin constant. Gas constant per molecule of a gas, which is represented with K. K is equals to R by N. Right? Here K value is 1.38 into 10 to the power 16 ergs, that is minus 16 ergs per Kelvin per molecule. And its value in joules is 1.38 into 10 to the power minus 23 joule per Kelvin per molecule. So this is also one of the important vsaq from states of matter. Next, molecular velocities. What is RMS velocity or speed? The square root of mean of the squares of the speeds of gas molecule is called as RMS. Root to mean square velocity or speed also you can say. The square root of the mean of the squares of speeds of a gas molecule is simply called as RMS velocity, which is represented with URMS is equals to under root of U1 square plus U2 square plus U3 squares and so on, UN square by capital N. N is nothing but total number of gas molecules. Or you can also write this expression as URMS is equals to under root of 3RT by M. or in place of RT, we can also write it as PV, because from ideal gas equation, PV is equals to nRT. For 1 mole of gas, if you take, that is n is equals to 1, you have to write is equals to RT, where n is equals to 1. So wherever RT is there, there you can write PV. So your RT is there, in place of that PV we can write. So anyway you can represent RMS velocity. Next, average velocity. So what is average velocity? The simple average of speeds of all the molecules of a gas is called as average speed, which is given by the formula U average AV. This is equals to U1 plus U2 plus U3 plus so on UN by capital N. Or in simple way, you can write it as U average, that is nothing but average speed, is equals to under root of 8RT by pi m. Even you can also write this as U average speed is equals to square root of 8 PV by pi m, because in place of RT we can also write PV, just now we discussed. Next, what is most probable speed? The speed possessed by maximum number of molecules present in a gas is called as most probable speed, which is equals to under root of 2RT by m. Or you can also write this as, that is most probable speed is equals to under root of 2 PV by capital M, also we can write. So this is about RMS, average and most probable velocities. Next, let us see the ratio between these molecular velocities. Give the ratio of RMS, average and most probable speed of the gas. So just now we discussed the different formulas. I substituted all this, then I got 1 is to 1.128 is to 1.224 is the ratio between different types of velocities of the gas molecules. Next. So one more important question is, what is Boyle's temperature? The temperature at which real gas exhibits ideal behavior for a considerable range of pressure is called as Boyle's temperature. Simply you can say this as, right, the temperature at which real gas behaves as ideal gas is called as Boyle's temperature. Next, critical temperature. So the temperature above which any gas cannot be liquefied even by applying high pressure is called as critical temperature. Generally, when high pressure is applied, gases can be liquefied. But here, the temperature above which gas cannot be liquefied even though you increase the pressure, so that temperature is simply called as critical temperature. This critical temperature is different for different gases. So here for carbon dioxide, the critical temperature is given, that is 30.98 degrees centigrade, or you can also write this as 31 degrees. You can write 31 degrees is the critical temperature of carbon dioxide gas. Next, coming to the critical volume. Volume of 1 mole of a gas at critical temperature is called as critical pressure. Volume occupied by 1 mole of gas at critical temperature is called as critical volume. Same way, critical pressure. Pressure of a gas at its critical temperature and critical volume is called as critical water pressure. Next, critical constants. So critical temperature, critical volume, critical pressure are collectively called as critical constants. Next, let us see 42nd one. Why pressure cooker is used for cooking food on hills? At high altitudes, atmosphere pressure is low. So liquids boil at lower temperature in comparison to that at sea level. So hence, pressure cooker is used to increase the boiling point of water by increasing the pressure in the cooker. Next, what is surface tension? So surface tension is important one. The force acting per unit length, which is perpendicular to the line drawn on the surface of liquid, is denoted by gamma, and it has a units that is joule per meters or newton per meter also you can say. So this is called as surface tension. Next, let us see what this is again. They have given what universal gas constant values. Next, 45th one. What is coefficient of viscosity or viscosity coefficient, and give its units? Viscosity coefficient is the force when velocity gradient is unity and the area of contact is unit area, then that is called as what coefficient of the viscosity. And here we have a formula that is F is equals to neta A dV by dz. dV by dz is nothing but a velocity gradient, A is nothing but area of the constant, and eta is nothing but viscosity coefficient. So these are the some of the important very short answer type questions from states of matter.